Have you ever looked at the ground and wondered, how can one patch of dirt be solid enough for a skyscraper while another turns into a soupy mess after a little rain? Well, it's a huge question for engineers, and the answer, it turns out, is all about finding a few key tipping points. I mean, look at this. You've got two totally different outcomes from the same basic material, soil. And the wild part? The only thing separating that solid foundation from a potential mudslide is just one simple ingredient, water. It all comes down to how much water is in the soil.
So, to really get a handle on this, you have to think about fine-grained soil as something that can exist in 4 completely different states. It's like a spectrum, really. Depending on the water content, it can go from being hard as a rock to, well, liquid mud.
Let's just walk through it real quick. When soil is bone dry, it's in a solid state, hard, brittle. Add a little water and it hits the semi-solid state, where it gets kind of crumbly. A little more water and you get to the really interesting one, the plastic state. Now it's workable, just like modeling clay. But if you add too much water, it goes right past that and becomes a liquid, basically a thick slurry.
Okay, but here's the thing. Engineers can't just eyeball this stuff, right? They need exact, precise measurements to know where those boundaries are. And that's where a set of tests called the Atterberg Limits come in. They are all about finding those critical tipping points.
So first up is the liquid limit. This is the absolute edge, the precise moment where a soil stops being plastic and starts to flow like a liquid. In the lab, they'll put a soil sample in this little cup, cut a groove in it, and then they literally tap it over and over until that groove closes up. That tells them the exact point of failure.
Then, on the other end of the scale, you've got the plastic limit. This is the point where the soil just doesn't have enough water anymore to be plastic. The way they find this is pretty simple. They roll the soil by hand into a tiny thread. The exact moment it starts to crumble and break apart, boom, that's the plastic limit. Now, this is where it all comes together. The real magic isn't just in those two limits, but in the space between them. You just subtract the plastic limit from the liquid limit, and you get one incredibly important number, the plasticity index, or PI. And that number, the plasticity index, is basically everything. It's what defines the Goldilocks zone for construction. It's that perfect range where the soil isn't too wet, isn't too dry, it's just right. It's strong, it's stable, and it's predictable. It's the sweet spot you want to build on. So we have these numbers, but how does that actually keep us safe in the real world? Well, understanding these limits is absolutely fundamental because if you get it wrong, the results can be, well, pretty disastrous.
It's a totally fair question. Let's get real for a second. What actually happens if an engineer gets this wrong, or even worse, just ignores these limits altogether?
Well, here's the danger. A soil